sorry. So I'll just go through the initial part again, the introduction. Okay, so we will be revising all the 8-week course content that we have done individually every week, and I will refer to the slides. I will put the reference to the slide numbers and the week number, so you can you can refer to those for better understanding and better explanation from the live interaction classes that we've had. So we were talking about different systems that exist in the universe. We have open, closed, isolated. In open, you have exchange of energy plus matter. In closed, it's only energy that is exchanged and transferred between two systems. Okay, so Earth is a closed system. Okay, so Earth is a closed system, and hence there is only exchange of energy, no matter is exchanged. But all these different systems or spheres of the Earth that we see, these are all open systems in nature. There is exchange of both energy and matter. Okay, so all these four open systems together make up the Earth, which is a closed system. Okay, next we come to Earth's energy budget. So the Earth's energy is derived from the incident solar radiation. Okay, so it is total incident radiation that we get is 342 watts. Now from this 342 watts, some percentage of the incident solar radiation interacts with the atmosphere as well as the surface of the Earth. Either they are absorbed or scattered or reflected back. The absorbed energy can be re-emitted back into the space, or then again this re-emitted energy can be absorbed by the atmosphere again. Okay, so there are different kind of interactions that take place with the incident solar energy and the solar energy that is given back. So we had done the exercise of radiation balance. I will put the slide numbers for reference to see how the number of units are actually managed to get to understand that how much energy is required for which process. Okay, so so this is a similar way that the different kind of units of the solar radiation, most of this is actually only in the atmosphere, and some part of it actually penetrates through the atmosphere, uh, and then the part which actually reaches the earth's surface, there is a separate kind of an interaction between the earth's surface, as well as again some part is re-emitted back into atmosphere, and so on. Okay, so now we come to the greenhouse gas effect that we have. Okay, so when we are talking about this Earth's energy budget, as I said, there are some interactions that are happening between the Earth's atmosphere and the Earth's surface. Earth's surface actually re-emits some part of the solar incident solar radiation that it is getting. So when it is re-emitting into like back to the atmosphere, if this incident gets trapped within the atmosphere, within between the atmosphere and the earth's surface, they tend to raise the temperature of the earth's surface as well as the earth's atmosphere. So that is when your greenhouse effect comes into play. So what are the greenhouse gases? So greenhouse gases, you have methane, and then you have the carbon dioxide, and you have the nitrous oxide, water vapor, as well as your CFC. So that those are chlorofluorocarbons. Okay, so these are the primary greenhouse gases, and most of them are occurring naturally, but some of them are also generated due to prolonged use of aerosols. So CFCs are a part of those. Okay, so these greenhouse gases actually absorb and emit radiant energy in thermal infrared spectrum. Okay, so in that in that relation they tend to increase the temperature. Okay, they trap the heat that the earth actually wants to emit back into the space. So if the greenhouse gases increase in number, okay, increase in quantity in proportion to the other gases, the trapped heat is going to increase to certain level, and because of that what we get is the increased temperature, the increased earth's atmospheric temperature and surface temperature. We are seeing more melting of glaciers, and then it leads to sea level rises. Okay, and that is giving us the entire arena of climate change that we are very much that is very much in focus right now. So this is the greenhouse effect. So over here mostly the long wavelength infrared light. Okay, so it will it tries to it is reflected back. This glass that we see, you can consider it as the atmosphere. Okay, and the inside of this greenhouse you can consider as the earth surface. Okay, so the long wavelength infrared light actually gets reflected back by the glass or the atmosphere that is present. Then there is the visible and short wavelength infrared pass. Okay, so there is a slide in the weekly content which gives you the electromagnetic spectrum. So you can see how the different wavelengths are actually differing, which region of the spectrum that we are talking about over here belongs to which wavelength. Okay, so mostly the one which is actually giving us the problem is that the conversion of this short wavelength infrared light into the long wavelength infrared light. Now as you can see that the long wavelength is always reflected by the atmosphere. Okay, so it cannot penetrate the atmosphere. So similarly, if the short wavelength infrared light gets converted into the long wavelength infrared light, now this long wavelength infrared light will start interacting with the atmosphere, and it will stay within between the atmosphere and the earth's surface. So it is not re-emitted back, and this actually causes the greenhouse effect that we know. Okay, so obviously when we are talking about the climate changes, there are greenhouse effect has it's both a natural process as well as kind of it is being exaggerated by human interference. But there are a few aspects which naturally have a control on the climate changes that we see. So the orbital motion of the earth itself governs the climatic patterns as well as the weather changes and the seasonal changes that we see. So as you know that we have two equinoxes and two solstices that are actually due to this orbital motion, and with respect to the earth's position and the sun. So the seasonal variations can be seen. Okay, so this is one of the primary reasons why we have different weathers. But even this orbital motion can get influenced by other aspects like the eccentricity of the earth's orbit around the motion, the tilt of the earth's axis, as well as the precision of the earth's axis. So when we are talking about the eccentricity, okay, eccentricity, so it the changes in eccentricity is happens over a long period of time. Okay, so it can take about 100,000 years for the eccentricity to change. So the change what happens is at first the eccentricity decreases. Okay, then it increases and then it comes back to its original position. So this entire cycle kind of takes 100,000 years. Then the changes in the tilt of the earth's axis can happen over a period of 41,000 years. Okay, so it changes between 21.5 to 24.5. So currently we are at at 23.5 degrees tilt, the actual tilt of the earth. So it will actually change, go all the way up to 24.5, then again it will change. So this entire process would take around 41,000 years. And the next one is the precession. So this is actually the wobbling effect that the axis, the Earth's axis actually wobbles when it is rotating as well as revolving. So this precession, so this entire that wobble that happens, it takes around 19 to 24,000 years. Okay, so these periods, these cycles are called Milankovitch cycle. Okay, Milankovitch cycles. So Milankovitch cycles, why is it important for us to know these? That because these actually dictate the glaciation and the interglaciation period. Okay, so all these eccentricity, tilt and precession, all of these actually have a control on the interglaciation and glaciation periods that the Earth actually experiences, okay, during its entire evolution. So it was studied in the past by the researchers, and they actually came up with this entire aspect that these cycles actually have an effect on the overall climatic pattern of the Earth. Okay, so now if we saw how the atmosphere actually has a role in the play of changing of the weather, as well as it can change, it can cause changes in your landscapes also with time, because overall the changing climate and the processes that result from these changes, all of them actually have an effect on the landscape formation or landscape variation that we see. So subsurface groundwater is one natural agent, which actually also has a role when we are talking about the changes that are done by water as a natural agent. Okay, so when we are talking about the subsurface groundwater, so actually the groundwater has the highest, it has a very high residence time, as in millions of, thousands of years also the water can stay in groundwater, and it is replenished, either very quickly, or it can take a long time for very deep groundwater to get replenished. Okay, so for the groundwater table is is actually the level at which the zone of aeration and zone of saturation is separated. So the groundwater table is actually the level of groundwater that we have. Okay, it's a measure of that. So we the for the zone of saturation to actually hold the water, the material that is present below the water table has to be porous as well as permeable. Okay, so in terms of your uh, porosity, we can see that the unconsolidated gravel has more porosity than your uh, coarse to medium coarse sand, and the least porosity, and obviously there are a number of different you can say material and rocks that have good porosity, like sandstone, or unconsolidated sand and silt. Fractured rock units also have a good capacity to hold, as well as help in transfer of water, but the least the least amount of porosity can be seen in in actually confined, or actually it is unfractured shale. Okay, so shale is a sedimentary rock, okay, and it is impermeable in nature. So if no water can go inside or through the shale, so there is no way that shale itself can hold water, which can be used as groundwater for us. Okay, and then obviously the zone of aeration, you have aquifers. So aquifers are those rock units which can actually store and transmit water at faster rates. Okay, so these store, as you can see, it can store water, and the since permeability of water is the permeability is at a good range. It can transfer water from one place to another. So having aquifers is very much required to have good groundwater levels at a place. Then you have aquetards, which can store water and transmit water, but in a very less quantity. Aquiclude has very low permeability, so it is almost impermeable in nature, and it can if there is an aquiclude present, you can see over here, if there is an aquiclude overlying an aquifer, so this aquifer is called confined aquifer. So you will have to somehow drill through the aquiclude to actually reach the confined aquifer. And for aquefuge, aquefuge is that rock unit which actually cannot yield, it does not store water, and it is completely impermeable. So usually bedrocks, okay, over here you can see the bedrock or the bottom of the the groundwater reserve that we have is actually an aquefuge. So now we come to the Earth's interior. Okay, so Earth's interior is obviously a layered structure. We have seen how these layered structures were studied and actually put forth in in scientific community at the start. So your crust is 70 to 40 kilometer topmost layer that is there of the Earth. So you have continental crust and you have oceanic crust, and this is mostly made up of silicon or silica and aluminium, and oceanic crust is mostly made up of silica and mafic minerals. Mafic minerals as in your iron, magnesium, manganese. Okay, so these are mostly called as mafic minerals. So you there is a distinction between this, okay, and then if we are only trying to characterize the different layers of the earth based on the composition, then you have crust, mantle and core, okay, because all of them have different kind of composition and different properties. But if we want to classify them with respect to the physical rheology of them, so you can have lithosphere, then you have your asthenosphere, and then you have mantle, and you have the core. Okay, and even in core you have inner core and outer core, because both of them have a different state of existence at that. Okay, so you have Cl Sema, as we said, lithosphere consists of the uppermost layer of the mantle, okay, and the crust, okay, both continental and oceanic. Then asthenosphere is actually partially melted, and it is a part of the mantle itself, but it exists below the lithosphere, okay, so it is partially melted. And then you have mantle, which almost actually takes up 84% of the entire Earth's interior. And then you have core. So core is mostly made up of minerals like nickel and iron, so you can call them as Nife composition. So you have outer core, which is a liquid, and you have an inner core, which is solid. Okay, so this is how the Earth's interior is generally structured. So if you want to understand how the density actually changes with depth, so the so actually density increases with depth, okay, increases with depth. So that means that crust has the lowest density from among all the layers. Then you have the mantle, and then you have the core, okay. And if we see the different kind of discontinuities that are present, so if you the discontinuity between upper crust and lower crust, okay, so this is called Conrad discontinuity. Then you have between the crust and the mantle, it is called the Mohorovic discontinuity. So we can just call it as a Moho discontinuity. Then between the upper mantle, okay, so there is a transitional, at a depth there is some transition between the, property or the characteristics of the material that is present. So with that we can get an upper mantle and lower mantle, and this discontinuity is called the rapidity discontinuity. Then between the mantle and the outer core, okay, so if we consider the core as a whole, if we write core as a whole, so it is actually this discontinuity is then called Gutenberg, okay. And the last discontinuity, that is between the outer core and the inner core, is actually called the Lehman discontinuity. Okay, so these are the different discontinuities, and all these discontinuities were found out by seeing or studying how seismic waves actually travel through the Earth's interior, and they are recorded at the other side from where the waves are actually generated. So I will refer to the slides for what has already been taught in the weekly classes. Okay. So now we come to the entire point of this course, that is the geomorphic processes. Okay, so the geomorphic processes can be categorized into endogenic and exogenic. Endogenic are those processes which are actually happening on the Earth's surface, not like the causes of endogenic processes are actually underlying below the Earth's surface. Okay, so the kind of the plate tectonic movements that we see, or volcanism, earthquakes, or the pushing of two plate boundaries or pulling away of two plate boundaries. So in all, the plate tectonics actually plays the most important role in the endogenic processes that we have. So you can have slow movements and sudden movements. So slow movements are essentially the plate tectonics which take a very long time to actually generate a new landform. And sudden movements also the are like they are also caused due to plate tectonics, as an underlying cause, but these can change the landforms at a quicker rate. So if you have obviously volcanism, it can in the duration of say a few hours, it can change the landscape at the place where the volcano has occurred. Okay, then you have exogenic. So these are mostly on the earth's surface. Okay, so these are actually happening on the earth's surface, and this is where we do study the different geomorphologies. So you have your fluvial geomorphology, so that is due to the running water. Okay, and then you have glacial geomorphology, so that is due to the glaciers, coastal, and then you have the aeolian. Okay, so we have covered all of these in throughout the different weeks that we had, and all the natural agents that we are considering over here, they actually do the work by eroding as well as depositing the eroded material that they have transported from one place to another. Okay, so this is how the geomorphology, it's actually the study of the changing of the landscapes and creation of new landforms, and all of these geomorphological changes actually occur due to the erosional and the depositional work that these natural agents are actually doing on the surface of the earth. Now, to first understand the endogenic processes, obviously continental drift theory was put forth to try to understand the how the different continents actually moved away from each other. And from the continental drift theory was the first kind of theory that tried to explain that how the continents have drifted away from each other, but it was not sufficient, as you can read over here that the driving forces that were proposed by Wegener were not enough, the magnitude of them were not enough to actually justify the continental drift theory. But later on, with study on magnetism and the mid-oceanic ridge in the Atlantic, so this actually paved the way to give a more refined theory that actually explain the sea floor spreading. So what they said was that the movement of the all the continents away from each other was compensated by the creation of the mid-oceanic ridges, and with the sea floor spreading and actually moving the continents away. So this was a very rough understanding, and obviously it has been modified over time. But the continental drift theory actually is the base of all the future plate tectonic theories that were brought forward. So for plate tectonics, um, the driving force for the plate tectonics is actually the mantle convection cell. So this was explained in the weekly class, but what is happening is actually the hot molten matter actually rises up, and because when it is rising up, okay, so it either drives the two plates away from each other, okay, in places where the hot material is actually going on top and it is driving the plates away from each other. But at another part, okay, so because of the nature of the convection cells, okay, so over here the material is actually it's driven down due to the changes in the densities of cold material and hot material. Okay, so these convection cells are actually generated because of the differences in the densities of the hot material and cold material, and these circular convection cells are driving the plates either away from each other or towards each other. Okay, so over here the plates will be uh, you know over here the plates is moving in this direction. So over here there will be converging of the plates, and over here there will be a divergence of the plates. Okay, so with respect to that, there are plate boundaries which have been classified. So for divergent plate boundaries, the plates are actually moving away from each other. So mostly the extensional processes are taking place. In convergent plate boundaries, the plates are moving towards each other. Okay, so they are going to actually kind of crash into each other, and they will form different kind of features. And there are another set of plate boundaries where the plates are not actually coming towards each other or going away from each other, but they just slide past each other. Okay, these also cause disturbances, and they cause different kind of features to be forming. Okay, so over here you can see at every point that is mentioned over here. Okay, so you can see what kind of plate boundary action is actually taking place. So ridges are created, the mid-oceanic ridges that we talk about is created at divergent plate boundaries. Trenches are created because of convergent plate boundaries, and transform faults, they do not but the sliding past of each other can also cause some kind of elevated mass to be formed. So these, and also you have different kind of volcanoes associated with different kind next to different kind of plate boundaries. So when we are talking about plate boundaries, this is just how we can depict. Actually, I think this image is a problem. This is transform boundaries. Okay, so transform boundaries are create this part is actually the transform boundaries. Okay, so it is hidden by the image, unfortunately. So you have divergent, convergent, and transform, and this is how you can, depict the different kind of plate boundaries. And sometimes there are people try to calculate the rate at which the plate boundaries or the plates are actually moving with respect to each other, and this is when this kind of depiction actually comes in play. So like this is a divergent plate boundary, and this is a convergent plate boundary. Okay, so this is one plate, this is one plate, and this is one plate. And similarly over here the direction of convergence is changing. Okay, so the actually this is the overriding plate, so actually this is going on top of this plate. Over here this plate is going on top of this plate. Okay, so this is how we can signify which plate is going on top and which is actually subducting under. Over here both of these and you can see that between the divergent and convergent you have a transform boundary. Similarly, between the two convergent plate boundaries over here, you have a transform plate boundary. So, all of these are actually understood on the basis of the relative motion and relative, movement of relative direction of movement of the plates. So, examples, this is these are good diagrams, very easy to understand diagrams of the different kind of plate boundaries that are there. So, for oceanic and continental, the example can be seen as the subduction of Nazca plate. Okay, so Nazca plate is the oceanic plate. Okay, so consider the Nazca plate as the oceanic crust, and South America as the continental crust. Okay, so Nazca plate is actually subducting under South America. So this is South American plate. So this is an example of that. For oceanic and oceanic, you can this trench that is created. Okay, so the very famous example is actually the Mariana Trench. Okay, so Mariana Trench is formed because of oceanic convergence. Okay, or subduction. Now, obviously, for continental convergent plate boundary, also the most famous example is the creation of Himalayas. So that is because of the convergence of Indian plate and Indian and Eurasian plates. Okay, and another example would be the convergence of African plate with the Eurasian plate, which actually forms the Alps and the Zagros in Iran. Okay, so it extends all the way from Alps to the Zagros. Now for divergent plate boundaries, okay, so mostly what we have is the creation of rifts or ridges. Okay, so rifts, usually the example of African Rift Valley is when actually the continental plate is actually getting pulled away from the other part of the continent. Okay, so there is a break in the continental plate itself. So that is when you have a formation of continental drift, and ridge is where a new sea floor is being made. Okay, so mid oceanic region, the Atlantic Ocean is an example of oceanic ridges, and they can go on for a very they can span few few thousands of kilometers also. So the entire mid-oceanic ridge actually forms the boundary between two different plates. Okay, and mostly the hot material is actually rising over here. So this is always this is kind of an active volcanic area. So you always have new the magmatic material being poured out at mid-oceanic ridges. And then obviously we have the transform plate boundary. The San Andreas fault is a very good example of the transform boundary. You can see over here the Pacific plate is moving to in the northwestern side, while the like it's mostly moving in the northern side, and the North American plate is moving towards the south. So because of the two different motions with respect to each other, the very long a fault is formed. Okay, so that is the San Andreas fault. Another kind of transform fault can be seen between North American plate and the Caribbean plate. So Caribbean plate is a minor plate, and so there can be transform boundaries existing between a major plate as well as a minor plate. Next we have the hotspot volcanoes. Okay, so Hawaii, as we know, is the chain of Hawaiian islands is actually formed because of the hotspot volcanoes. So the actually because of the movement of plates over the mantle, over the asthenospheric part. Okay, so there are few places where there is constant hotspot plumes that are present. The plumes do not move, but because of the movement of the plates over these plumes, you get a chain of volcanoes. Okay, so you can kind of see which how the movement of plate has taken place if you date all the islands. So if either it is moved in the northern side or the southern side, you can understand that if you try to date the individual islands of such chains of volcanoes or chains of islands. So over here you can see that this is the trajectory of the this is the present spot where the hot spot is actually present and is active, and this is the trajectory that the continental plate has actually or the plate, not continental plate, the plate that is actually consisting of the Hawaii the region, how it has deviated. Okay, similarly over here you can see how the paths have been taken place. Reunion hotspot plume that is actually related to the Deccan Traps volcanic activity that had taken place. You can see how even how the path has changed. Okay, so that means the India actually moved over the reunion spot towards the north. Okay, so this is the trajectory that India has followed, and the evidences can be seen in different kind of islands, volcanic islands. Okay, so this is the understanding of how the hotspot volcanoes are formed. Okay, so this is the plume that rises. Okay, so it can generate from the outer core itself, and because it is kind of generating at such a depth, it does not really move a lot, but it leaves a volcanic trail when the plates are moving over the plume that is existing. So now let's come to the different natural agents and what kind of geomorphic changes they are going to make. Excuse me. Okay, so the general form, or the general way the geographic kind of changes that are taking place, which are changing the landforms and the landscapes on the earth's surface. So this entire cycle can be called as the geographic cycle. Okay, and it starts at at a stage where mostly what we the processes that are predominating the origin or the youth part of the any natural agent that is going to work is erosion. Okay, then it comes to the mature stage where the erosion rate becomes slower. Okay, and there is some deposition also that is happening, and at the old age you have almost negligible erosional activity that is taking place, and most of the work that is, or most of the changes that we see, is because of the deposition of all the material that has been carried down from the youthful and the mature stage all the way up to the old age stage. And rejuvenation happens when you have the combination of a natural agent related geomorphic changes as well as some tectonic processes that are taking place. Okay, so any upliftment or subsidence uplifting of an area or subsidence of an area, along with the either fluvial, aeolian, or glacial coastal geomorphic processes that are taking place. Okay, so that there you can have rejuvenation, and when rejuvenation happens, the rate of erosion can increase than what it was before the tectonic process had actually, or the tectonic event had taken place. So the first natural agent that we will be that we had studied was the river, the running water, and it was related to fluvial geomorphology. Okay, so fluvial geomorphology is the study of the processes which develop and change the landform and landscapes due to rivers or running water. Okay, so when we are considering a river, so river itself can be divided into different stages. So you have the upper course, middle course, and lower course. So usually with respect to the elevation, this has been taken. So we can understand the upper course is where you have the origin as well as the youth stage of the river. Okay, so middle course is in the kind of the middle part, or the mature stage of the river is taking place. Lower course is mostly associated with the old stage of the or the later mature stage of the rivers that we say. Okay, so if you take a cross section at each of the end of the courses, or in the middle of the courses, so in upper course you can see that mostly erosional work is taking place, and you get very deep but less wide V-shaped valleys. In the longitudinal profile, the incision, or the kind of the work that is required to cut down the valley to very deep deeper depths is not done, because it is at a mature stage. The velocity has kind of the rate of flow of water also decreases a little, and what you get are U-shaped valleys, and the width of the river channels increase when it comes to the middle course of the river, and when it reaches the lower course or the older stages, you will see more wide river channels, and while the depth is maintained as it is seen in the U shape, but it is not the width is much more compared to the depth. So, and it's not just the width of the channel, the entire kind of the banks of the rivers also span all laterally across for many kilometers. So, to understand the what sort of features that are formed, there are a few things which actually control uh, what sort of work is going to be done by the river. So, it depends on discharge. So, you have the upstream. So, this is the upstream, and this is the downstream. Okay, so in the upstream mostly you have low discharge, but you have larger rock fragments can be carried by the water in the upstream parts, obviously, and the gradient of the river is also higher in the upstream part. And with the when the river is coming downstream, so downstream will always have more discharge, the width increases, the channel depth also increases, keeping other factors in balance, and the average velocity, the increase is not very like in the downstream. Obviously it will have more velocity than the upstream part of one segment of the river, and more load, like the finer sediments and the medium sized sediments, the quantity of these sediments increases in the downstream part of the river. Okay, and over here you can see this is kind of the origin or the source of the river, where you have glaciers, and then when it comes down, it starts, forming these sinuous channels that we see. These are also called meanders. And around, in the mature stage, in the early mature stage, tributaries contribute and join the main river channel, increasing the width of the channel itself. Then you can have different kind of depositional as well as erosional features. So you have levees, you have oxbow lake, and then you finally it forms a delta or an estuary near the mouth of the river, or where it actually meets the sea or the oceanic body. So for river, to understand uh, the uh, relation of the river channel that is flowing, and the either the slope or the what kind of geology is present over there. So people have tried to form indices or quantitative measures to understand. So sinuosity ratio is one such quantity where you can understand whether the channel is straight or sinuous or meandering, and with their whether if it's a straight one, so you can people have tried to correlate it with the slope, the channel slope, as well as the elevation change that is seen between the river segment that we are calculating the sinuosity ratio for. And obviously with with changes in the slope, as well as changes in the geology that is present over there, or any kind of tectonic changes that is seen, you can have straight channel converting into sinuous and then converting into meandering, and meandering channel can again become a straight channel. Okay, so sinuosity ratio gives us an understanding of how the river channel is responding to the different topographical and tectonic changes that occur. So there are a few channel patterns, basic channel patterns. So you have straight, you have sinuous, then you have meandering, then you have another index, that is braided index. Braided indexes, these are actually point bars that are formed due to deposition of sand or silt, okay, in between the river channels, so in the middle of the river channels. So if these bars increase in numbers, so what the water tries to move in between these bars, okay, and for that the channel also widens itself. So with time, actually, when it goes from the say early mature stage to late mature stage, early old age, the braiding or the the braiding of the river increases. Okay, so over here you can see there are lot of point bars that have been created, and hence the braiding index is reaching 4.50. Okay, so all these channel patterns can be seen to change as per the channel stability, the amount of sediment supply that is carried by the channel, or the channel gradient, or the channel stability, and the sediment, the capacity of the sediments to be carried. Okay, so this you can see the correlation between the different factors that control the channel patterns. Then there are again channel type we have. So this is 1, this is 2, this is 3A, this is 3B, okay, and this is 4. So over here you see that 1 you have straight, okay, so where mostly you have suspended load, you don't have a lot of large rock fragments, or sediments which cannot be carried by the water in suspension mode. Then when the load kind of changes, it has a mix of loads. They start depositing towards the banks of the rivers, and with you can see that with changing channel patterns, you have meandering meandering pattern but with suspended load, you have meandering pattern with mixed load, and then with you have braided channel patterns, okay, when you have more of bed load present. So bed load as in the load that cannot be carried by the water, and it starts settling down in the channel bed. Okay. So then, because we said that the channel patterns that we had discussed before actually is mostly controlled by the kind of the channel stability, the slope stability, the amount of sediment that it can carry. Now drainage patterns are created because of the underlying geology that is present over there. Okay, so you can have two types of drainage patterns. You can have discordant and concordant. So concordant is when the drainage pattern is it is following the structural and the geological features that are present over there. So if there is a fracture that is present, okay, and mostly the fractures are controlling the evolution of the drainage pattern in that place, so that would become a concordant drainage pattern. So you have consequent, subsequent and resequent streams. So consequent, as you can understand, is like a consequence of the direct consequence of the topography. Subsequent is it is developed after the consequent stream. So again it is following the present prevailing topography that is present. Obsequent is it actually follows it flows in the direction that is opposite to the master consequent stream. Okay, so while it would seem discordant, but even though the flow direction is different, it will still be controlled by the topography or the structural feature that is present in the opposite direction of the flow. Okay, a flow of the consequent stream. Resequent is it actually flows in the same direction as the consequent stream, but if there is a creation of new relief or change in the relief, then what happens is it will get controlled by the new relief that is present over there. So those are concordant. Then you have discordant. So discordant is are those drainage patterns which have which flow in a way that is not resembling the topographic or the structural features of the area of the underlying rock. So you have superimposed drainage patterns and antecedent drainage patterns. So superimposed is suppose there was a certain drainage pattern that was developed before, but it got eroded. Okay, and the newer drainage pattern, newly developed drainage pattern has it differs from the eroded drainage pattern. Okay, so you can see the drainage pattern has it is not totally going with the past strata that was present, and the present strata and the past strata or the drainage pattern that is visible over there has some kind of offset from each other. And antecedent is usually the drainage pattern, the changes in the drainage pattern that we see due to tectonic events, either folding, or you have one part has uplifted and one part has gone down, and because of the uplift, okay, when the uplift was taking place, the river could adjust its rate of flow, or the change in the change its course in a way that it actually tries to compensate for the uplift that has happened. Okay, and it will be maintained. So if a river is cutting is flowing across a plain area, but there is a sudden uplift, but the drainage the uplift was so slow that the river actually got time to still flow in a straight manner, okay, and cut through the uplifted portion, and you can see that then this kind of drainage pattern can be called as an antecedent one. Okay, so drainage evolution, as we said, since river itself has youth, mature and old stage. Okay, so even the drainage pattern that is associated with a river also evolves in different stages. So you can see at the start you have very low number of branching of the main stream, and then with time you see the branches have increased and lower order streams have they also increase in numbers. And then this is the maximum extension that is reached by the river basin or the river which is causing the drainage pattern. And with time and with decreased flow to certain streams, so some streams they are lost, and sometimes due to diversion or changes in the direction of the flow, some streams actually come together and join a bigger stream than it was before. So what we have is the streams. Okay, so you have different stream orders. So the smallest one, which does not branch out any further, is given the smallest stream order. Okay, so you I will refer the the slide which is associated with this, so you can see it better. I think the diagram over here has been uh, you know there's an issue with the dimension of it. So over here, so you can calculate the bifurcation ratio. Okay, so it is defined as the ratio of the number of streams of a particular order to number of streams of next higher order. So you can understand how much branching has occurred. So we had tried to find the bifurcation ratio for these two drainage patterns. So I will refer back to the slide so you can easily understand that. Okay, so some drainage patterns have been classified, and they have been they have been given nomenclature. So you have dendritic, parallel, trellis, radial, annular, rectangular. So these are different kinds of drainage patterns which are seen very commonly. So dendritic, it's irregular branching, and mostly they form in gently sloping areas, and the geology or the rock that is present there, they all belong to the same type of the rock, so it is homogeneous in nature. So that is when you have dendritic patterns. Parallel patterns, they develop in areas with steep slopes. Okay, so the sides of the mountains can be one place, and obviously because of that they form elongated landforms, and they are running parallel to each other. Then you have trellis. So these are again formed in areas where you have dipping strata, or you have folded strata. So these streams are actually, the streams are kind of flowing in a linear the main streams are flowing in a linear pattern, but then the subsequent streams are actually forming also have a parallel kind of relation with the other smaller streams that we see. So minor tributaries also flow parallel to each other, and the main streams are actually parallel to each other over here. Okay, so these can happen in dipping or folding sedimentary or meta sedimentary rocks. Then you have radial. So radial, usually these streams originate from a central point of the region. So you have volcanoes, domes. So they are examples where you can have the radial drainage pattern. Annular drainage pattern, they kind of form like a ring, they form a ring, and this usually happens, suppose there is a dome and there are fractures that are occurring on the dome. So the stream, after it originates, it tries to flow through through these fractures, and if you look from the top, they actually kind of form like a ring. Then you have the rectangular ones. So these usually flow through joints and fractures in existing rocks that are present, rocks like sandstone and quartzite. Sorry, yeah. Then you have other less common but still identifiable drainage patterns like pinnate, angular, centripetal, and subdendritic. You can see all the different kind of drainage patterns that are sketched over here. So now we will see some of the erosional features that are created by due to fluvial geomorphic processes. So you can see over here you have oxbow lakes. You can see how it is. You can find it in within the the drainage basin that has been created. Then you have these are actually canyons. Okay, so canyons, as we know, Grand Canyon is one of the very good examples which has been created over millions of years because of the erosive action of the river, which is still you can see it flowing through the Grand Canyon. Okay, so you have natural levees, you have terraces that are formed, okay, and then you have the natural levees which are formed over here, then a terrace over here. So these are all erosional features associated with geomorphic action of the rivers. So how Oxbow Lake, so this is a meander that is being formed. Okay, so with time what happens is this part keeps getting eroded. Okay, so the outer banks of the rivers get eroded, and this patch of land is totally eroded away, and this segment of the stream and this segment of the stream join together. Okay, and with time what happens eventually is the water the supply of water to this curved feature is actually stopped, and then this forms a lake, okay, separately. So this is how oxbow lakes form. It's more of an erosive action of the rivers to in the outer banks of the rivers, which actually separates out the meander from the main river channel. You can see how rivers are actually causing the formation of different valleys over here. So this is a V, then with time it can deepen into a U, and again with time, but more of meandering action that happens, the development of meandering channels, it can turn into a flatter valley. Okay, obviously waterfalls and rapids are also created mostly by the erosional work of the river, when there is a sudden change in the slope you know uh, along the course of the river. So some depositional features, as we know that the flood plains that are associated with the river is actually it's made up of different kind of depositional features, like you have natural levees, meander scars that we saw. So the Oxbow Lake, if it dries up, what you are left with is a portion of the past meander. So that is a feature that we see in the floodplains. Also Oxbow lakes are there. Okay, and then you have bar deposits. So bar deposits mostly occur either along the banks, okay, so along the banks of the river or in between the river channel also. So when you have a lot of sediment load that is being carried down, and probably it meets a certain drop in the flow of the rate of the flow of the water in the channel, so then they start getting deposited and they get built up in between the river channel itself. Okay, so there are different kinds of bars related to what is the position of the formation of these bars. So the point bars over here you can see, so these are point bars, and these are longitudinal bars that form in between the channels. So depositional features, obviously, so you have natural levees that develop on the floodplains, and you have alluvial fans that develop near the foothills. Okay, so the point where the river exits the elevated lands, and it comes into more plain region, okay, like the foothills of Himalaya. So due to the sudden drop of the channel, the slope gradient, also the channel velocity gradient, so it or the sediment that has been carried, okay, so because the river is at a higher velocity when it is coming down the elevated areas, it can carry all of the sediment that it has eroded away, and it is transporting. But when this sudden change in the velocity as well as the slope gradient happens, the sediment actually spills out and it forms and it gets deposited in this fan manner. Okay, So this is the present area where the deposition is happening. Okay, so that is the active lobe. And previously, probably when the channel was much wider in in nature, so it might have formed the previous or the inactive lobes that are shown here with the dotted lines. Okay. Then the most important depositional feature associated with the fluvial geomorphic processes is the development of deltas. So you can have arcuate, Birdsford, Cascade, and estuarian. So these are all different kind of the shape. These are classified with respect to the shape. So the Ganga that we have in India is actually a type of arcuate delta. So there is a tidal delta also. So tidal delta is different than your river deltas. Okay, so these are mostly the river deltas. Okay, so these are not tidal deltas. River deltas are mostly formed when because of an interaction of the tides and the currents, and the sand also that is carried by the river, but they are shaped because of the tides and the currents. And mostly the formation of river deltas, the activity due to the the activity due to the currents, wave currents or the tidal currents is much lower for the river delta to be formed and preserved. Okay. And then obviously flood intensity is important for us to know, because rivers are prone to flooding, and when the flooding will happen or at what point of the discharge content of the flooding can happen, it is we can try to study that by studying the shape of the flood hydrographs. So over here you can see the correlation and how. So if the lag time, this is the lag time from normal discharge point to peak discharge. Okay, so the lag time can help you in understand after at what point of discharge or after how long will the peak discharge will be happening in the river, and whether the river itself can hold that discharge or not. This is the storm hydrograph or the flood hydrograph. Okay, so you can see that the steeper the rising limb, okay, so the more likely the flood can occur. Okay, so as we said, this is the lag time. Okay, so lag time between the peak rainfall and the peak discharge time. Okay, so if this is shorter, that means flooding obviously is the flooding is definitely going to happen. But if this lag time increases, that is the rising limb is actually gentler in nature, so uh, uh, the certainty of floods occurring actually reduces. So now we try to see the tectonic geomorphology part. So for that we have to know the different kind of faults. So you have normal faults, you have reverse faults, and then you have these strike slip faults. Okay, strike slip faults. So we had already explained this in the previous classes. So in normal fault, you have a hanging wall. So that the block that is on top of the fault plane that we see here, this is the fault plane. Okay, so the block that is above the fault plane is called hanging wall, and the one that is below the fault plane is called the footwall. So if the hanging wall goes is moved on top, and the hanging if the footwall has moved on top and the hanging wall has moved down with respect to the footwall, then what we have is normal fault. And if it is the vice versa, that is the hanging wall. As you can see, this is the fault plane. Okay, and even now the hanging wall is on top of the fault plane itself. So the hanging wall, if it has moved on top with respect to the footwall block, then what we have is reverse fault. Okay, so thrust faults is when this when the angle between the fault plane and the horizontal is actually very it's less, so less than 45 degrees, then you can call it a thrust fault. And for strike slip fault, this is similar to the what we had seen in transform plate boundary, so where the blocks are actually moving past each other, so they slide along past each other. So those are the different faults. And for tectonics, we have large facets and smaller facets that develop, okay, at the mountain front that we see. So larger facets actually imply that there is recurrent faulting, and these are tectonically active faults, okay, while this smaller facets will signify that there is less tectonically active uh, less tectonically active fronts. And because the development of drainages has happened much more than the development of the facets or the changes in the tectonics that we see in that area. Okay. Now, as I said, for tectonic geomorphology alone does not, have an implicit role. It will work in combination with a different, kind of geomorphology. So, fluvial geomorphology or the geomorphic, features due to developed due to fluvial geomorphology can change due to the role of tectonics in that area. So the changes in channel patterns from 1 to 3, 4 and 5 can happen even when we have variation in the tectonics of the area. So when you have tectonics playing a role in changing the landscape, you can have two types of processes. So one is aggradation and degradation. Okay, so aggradation is mostly building up, okay, building up of landform, and degradation is as you can understand from the term itself, so it is actually destroying or okay destroying the landform. So aggradation happens, then you have increasing in the base level of the topography that is present over there, and degradation actually decreases the base level. So mostly when you have a lot of sediments present in the river, a lot of sediments is being carried by the river, aggradation can happen more dominantly at that time. Degradation happens in sediment starved rivers. So when there is not much sediments present, so the rate of flow of the river is actually higher, and it can erode more and degrade more. Okay. Then you have associated with deposition, aggradation building up. So deposited, the sediments are getting deposited, and degradation is associated with erosion. We already talked about it. And when there is a decrease in the kinetic energy of the of the river, it can start aggrading or depositing. Whereas if there is increase in the kinetic energy, the response of the geomorphology over there changes to degradation. Okay. So over here you can see with the there is an uplift in the middle section over here. So what happens is, because of the changes in the base level that we see over here, okay, so this part will start, there is lowering of kinetic energy over here, and hence there will be and also maybe obstruction of the more sediment can flow over the uplifted area. So what will start happening is there will be aggradation in this part, and because of this base level, it will try to get the base level down to what it was before. So the river over here starts degrading the topography present over here. Again over here, because with degradation the sediment supply would have increased, but because the base level has gone down over here, it will start aggrading over here. Similarly, in fault, now since this has gone on top, this is the footwall and this is the hanging wall, so this is a normal fault situation. So over here you can see that the since footwall has it has got it has gone up and it has got uplifted, so over here you will have degradation, whereas the hanging wall, where it has gone below the base level, it will try to the river will try to build up to the base level. Okay, so it will try to increase the base level. Then we had seen different kind of geomorphic indices which actually can tell us whether the area is, you know, less tectonically active, tectonically active, or you know, it is tectonically or it is, you know, predominantly changed by tectonics. Okay, tectonically active region. So you have mountain front sinuosity. So how how sinuous is the nature of the mountain front. Okay, so that can tell you whether it is mostly dominated by tectonics or the other geomorphic processes are dominating over there. Also valley floor and valley height ratio, all these have been explained in the previous weekly class. So this is just like a you know, summary of all. So to understand each of them, you know, separately, I will refer the slide numbers and the week in which this was taught. Okay, and mostly then you have the stream length gradient index. So these three were mostly explained during the weekly content also. So these actually help you in understanding whether the geomorphic processes are more dominant along with the tectonics, or it is mostly all the landscape that has been developed is controlled by tectonic processes, you know, with a in a major proportion. So as you can see that, you know, there are some changes in the position of the channels when there are, you know, tectonically active tectonic processes that are taking place. You can see how the channel is shifting from, you know, the uplifted area to the down to the subsided area, as you can see. Okay, so this is down tilted area, this is the up tilted area. So the tilt has happened. So maybe this region actually had got uplifted, and the area you know, away from the uplift point actually tilts downwards, and then you can see that the channel also moves yeah, as per that. So you have an asymmetric river position in the valley itself. Okay, so the valley itself, you can see, has got an asymmetry to it, and because of that, these are, you know, some of the meanders or, you know, paleo channels that have been kind of abandoned by the channel, and the channel has now moved in the you know, towards in the downslope region of the uplifted area. Now there are a few elements associated with the fall. So the major one is the scarp. Okay, you can see the scarp, and how you can see the channel actually kind of you know, tries to accommodate for the change in the elevation over here, the slope gradient over here. So you can have fall scarps, you have warped or folded surfaces, pressure ridge, back tilted or back tilted surfaces, or the most important one that we see, offset or deflected streams. Okay, so if you have a strike slip fault, so if the river was flowing from in between, so now the course has kind of, you know, got offset or it has got deflected, okay, due to the existence of a fault. And you can see over here, so this part is actually the fault scarp. Okay, so you can see how the landscape has changed over here because of faults. So active faults, as you can see over here, you have an offset stream, or you know, over here also you have an offset stream. Some places the stream is completely the flow of the stream is completely blocked because of the development of the stream of the fault scarp also. So this is where you have your active fault zone right now, and these are the different features that are associated with active faults. Okay, and then there can be smaller faults can link together, and they can kind of, you know, grow together and form longer faulted regions because of this. Okay, so you can have progressive fault linkage, and because of that, these smaller faults can together coalesce together and form bigger longer faults, and displacement along these faults can happen in future. So now if we go to the glacial geomorphology, okay, so we can try to see whether we are in the glaciation period or the interglaciation period by understanding the isotope ratio between O18 and O16. Okay, so when the glaciers are growing, so your O18 is going to be richer in ocean since it is not that easily evaporated, and the evaporated O16 precipitates out, and then they turn into glaciers. So if your glaciers have more O16 and your seawater will have less of O16 but more of O18 because of this. Okay. And glacier can move either as a basal slip where the bottom of the glacier is actually some amount of it melts and lubricates and helps in the slip motion of the glaciers on the bedrock, whereas when the bottom of the glacier is not melted even a little bit and it tries to move over a bedrock, it will due to frictional action, it will try to scrape along the bedrock, and it will also pluck out some rock fragments and carry with it downwards. So there are these two types of movements by glacier. Then obviously as you can have some types of debris actually are carried by the glaciers at different levels or different layers of the glacier. So you have supra, that is on top of the glacier, end glacier is in within the glacier itself, and then you have subglacial, that is at the bottom of the glacial like on the rock bed. Okay, so you can see over here all the different sediments being transported by the glaciers. Then you have two types of glaciers. You have continental. Okay, so examples are Greenland and Antarctic, so they are large masses. And then you have alpine, so mostly these are found in mountains, so in Himalayas and Alps. Okay, so all the glaciers that are formed in the valleys, in mountain valleys, so these are called alpine glaciers. You also have another one, that is Piedmont, which is explained in the weekly class. So again, glaciers have erosional, they do erosional work, and as per the erosional work that they do, and at the stages of the glaciers where these happen, you can have different kind of features like cirques, and cirques are these areas where the glacier is actually originating and then they move from there, and then the boundaries between two cirques is called an errate, and then if there are three cirques, okay, and they erode the mountain, the back of the cirques are getting eroded. So if there are three cirques which are eroding and moving backwards, then what they form is a horn, which is like a pyramid kind of a structure. Then you have Paternoster Lake, like these are all kind of a series of glacial lakes that are joined together and form like a linear lake. Then the other the important kind of, or the vast type of landforms that are created by glaciers are the U-shaped glacial troughs or U-shaped valleys, and the hanging valleys. So you can see over here, so this entire this entire part is actually the U-shaped glacial trough, whereas all these smaller valleys that are actually feeding into the U-shaped valley are called the hanging valleys, because as you can in just visualization you can think of these are actually hanging over the U-shaped valleys. Then obviously you have another feature called coal. So this is if two cirques, the erosion that is happening because of the glaciers movement in the cirques. Okay, so what happens is after a certain time the arrate between them, okay, so the boundary between them also gets eroded, and that is when a coal is formed. Okay, so the two cirques come together and form coal. Then you have fjords. Okay, fjords are kind of troughs or valleys that are created by glaciers, but then they are drowned by the ocean. Okay, so over here, so this is the fjord that is present over here. So the water that is present on the fjord, so the top layers will be cold and the fresh water from the melted glaciers, and the bottom part of the fjords will actually be the salty, the sea water or the ocean water uh, where it is formed. So mostly these have form in the coastal part of uh, glaciated land. So if you like Norway has a lot of forts created. Then the the depositional landform. See, the most important glacial landform is the moraines. Okay, so there are different kinds of moraines based on where they are forming. So you have lateral moraines, so those are at the sides of the glaciers. Then you have medial moraine, where two lateral moraines, they join together and form a moraine. So that those are medial moraines. So they are occurring here in between. Then you have the ground moraine. So these are actually the rock fragments and everything that is occurring beneath the frozen ice of the glacier, and then they are just they settle down when the glaciers melt. Then you have the terminal moraine. So this is the the sediments that have been left behind when at the snout of the glacier. Okay, so at the end of the glacier they can, because that is why they are also called end moraines. Then you have recessional moraines. So this is a type of terminal moraines, but it could happen, it could occur at different stages of melting of the glaciers. Okay, so maybe the glacier has melted and it has formed an end moraine, but there has been an increase in the transport of the glaciers, or the more with time there has been creation of more glacial ice, and the glacier has moved further down beyond the previous end moraine where the end moraine was created. So a new end moraine would be created. So these can be called as recessional moraine. So you can see over here, this looks like an end moraine, but it is developed behind this end moraine, terminal moraine over here. So these are called recessional moraines. And some more depositional landforms that are associated with glaciers are eskers, drumlins, then you have kettle lakes. These can be mostly seen in areas with continental glaciers. Okay, so these are like small swarms of hills of these sediments that are deposited, and these are all melted glacial waters. And eskers are kind of a ridge, but they are sinuous in nature. And kettle lakes are as I said, they are formed from melted glaciers. And then you have outwash plains. So this is similar to how flood plains are there, all the sediments, the very small size sediments get just deposited and when the glaciers are melting. Then we come to the coastal geomorphology. So obviously this is due to the action of the waves on the along the coast that happens, and because of winds, waves, currents, as well as sea level changes. So all these play a role in creation of coastal geomorphic features. So obviously you have waves that are forming, and you can have wave refraction, wave diffraction, and wave breaking. So these are all the different wave processes that take place. And again, coastal currents, different kind of coastal currents play a role in shaping of the coastal landforms that are developing. So you can have a longshore current, and because of the longshore current you can have uh, the sediment movement is associated with the different kind of currents. So over here, longshore current has mostly parallel movement of the parallel to coast movement of the sand or the sediments. Then you have the swash and the backwash. So over here also you can have kind of a periodic kind of sediment supply and sediment reduction. Then longshore current we have seen. Then you have littoral drift. So littoral drift can cause, you know, changes in the orientation of different features. Then you have different zones. So you have coastal zone. It's the transition zone between where the land is meeting the water. Coast is from the coastline and towards the inland, where the major change of topography that happens. Then you have the shore face, and lastly you have the continental shelf. So as we move from the waterline to the towards the deeper ocean part. Okay, so these are the different coastal zones that we see. And so the beaches are actually a large depositional feature that is created by the coastal geomorphic processes. But beach profile can, you know, differ with seasonal changes also. So in summer the beaches actually grow in size, whereas in winter a lot of erosion happens due to the changes in the wind speed and the storm occurrences that happen in coastal areas. Okay, so coastal obviously the erosional activities can happen due to corrosion, abrasion, solution attrition, hydraulic action, and most of the features that we see in coastal areas are actually erosional, are due to the erosional effects of the water, and along the beach mostly the depositional landforms are seen. So for the erosional work to happen, okay, so if there are the softer part, okay, or the softer regions along the coast get eroded faster than the harder than the areas where you have harder material or rocks that are present. So the place which gets eroded faster, the softer part actually turns into a bay, and the harder section of the coastlines are called headlands. So headland is a section of rocky coastline, and bay is actually the indentation of the coastline between two headlands. So at the at the headland portion of the coast, you can have features like cliffs. Okay, so where you have the waves eroding the base of the coast, the headland coast, and it will first create a wave cut notch, and this wave cut notch gets further eroded. And when the top part of this wave cut notch is not supported by the eroded bottom part of the headland, so it collapses, or it can create caves and different kind of other features. And the steep rocky face, okay, where the land is meeting the sea, that is called a cliff. And you can have obviously wave cut platforms that are developed due to the kind of extension of the wave cut notch towards the inner part of the headland. And then, as I said, that with more and more erosion of the bottom of the headland, you can have caves which are forming. And then when the caves itself get eroded from both the sides, you can have an arch that is forming. And with further erosion of the arch, the roof of the arch it cannot be supported, and then it collapses. And what you are left with when the roof between suppose this was an arch before, so if the roof over here was not supported, it collapsed over here, so what you are left with is a stack, and it is also an isolated portion of a previous cliff that was there. Okay, and the stack, sometimes if this stack gets eroded in the from the bottom part, okay, and then what happens is this part cannot be held on anymore, and this will fall, and then it can what it leaves is a stump. Okay, so that too is an erosional feature related to the geomorphic processes. Okay, then depositional landforms, you have spits and sandbars. Okay, so spits are formed as an narrow long ridges, and they separate the sea from if the spit actually elongates further, and it can separate a part of the ocean, part of the sea from the main sea, so you can have bays that are created because of that. So spits can create bays, and then sometimes this water which is trapped behind the spit can create salt marshes. And then you have bars. Okay, so these are just elongated deposition of sand, and they can also separate the sea from a tiny part of the collected water body behind, like lagoons. So that is something that the bar can develop into. Then you have tombolo. So this is actually the kind of a ridge that is connecting an island to the main coastline. So this is a tombolo. And then you have obviously the important depositional feature, that is the beach and the beach dunes. So because of the because in summer, when the beach is actually growing, some part of the beach, the dunes are actually occur at the further back from where the water is actually doing having its wave action. So dunes are formed at the back part of the beach profile. Then you have something called berm developing. So berms develop during because of tidal action that is happening. So when the water is actually kind of washing over the beach, it is obviously it has some amount of energy, but when the water is receding back, it does not have enough energy to take away all the sand that is present on the beach. So what we get is an elevated kind of feature with a very steep slope. Okay, so this is called a berm. So this over here you can see, this is the berm crest. So this is an elevated part of the beach, and this is the beach face, but you can see that there is a steeper slope that is present. So then you have lagoons and estuaries. Lagoon is different from estuary from the way it is forming, and coastal lagoon, it is separated from the ocean, but it is connected by an inlet, whereas an estuary is where the freshwater river is meeting the ocean. Okay, and it is not it can be brackish in nature, but it cannot be completely salty. Okay, so the differences that happen occur between because of the flow dynamics of the water bodies. Okay, so estuaries are usually deeper than lagoons, and in estuary, because of the river dynamics as well as the wave action, so the flow of the water is faster than it is in lagoon. Okay, so barrier islands is when a lot of sandbars are actually they grow, and you have a continuous deposition of sediments, and it forms parallel to the shoreline. Now we come to the last part. So this is what we had done in the last class itself. So it is Aeolian geomorphology. So it is all the features, landforms that are created due to the action of wind, and which are shaped by wind. So mostly they occur. Mostly they occur in arid, extremely arid or semi-arid regions, and mostly these are desert areas which have very low rainfall, annual rainfall, and they have very low vegetation. Okay, so these are the areas where the action of wind can happen over larger areas without any um, kind of obstruction in the movement of the wind, and that is why the winds over there can have a lot of control on how they shape the landscape in desert areas. So how the deserts are formed, we had explained that it is formed in the area that is called the rain shadow area, because of orographic precipitation, most of the moisture from the air is actually precipitated out in the upwind part of the of the movement of the wind, and this is the downwind. Okay, so this is the upwind. So most of the precipitation is happening in the upwind part of the mountain that is present, and the downwind, part of the mountain has drier, warmer air, and it has very low moisture. So if there is not much moisture that is present, it cannot sustain any vegetation in the downwind part. Okay, and so this is where your desert is forming, where the rainfall is uh, under 250 millimeter at an the annual precipitation is below 250. So the wind erosion and associated landforms. So obviously for the ability of wind to erode depends on the velocity of the wind as well as the surface roughness. So if the velocity has to be very high for the wind to be able to carry the material with it as well as erode the existing features over there. Okay, and but if the surface roughness means how many obstacles the wind is facing. If there are a lot of vegetation or instances of human settlements present over there, so the wind is going to face obstructions, uh, and then the velocity decreases, and the the capacity of the wind to erode further decreases because of that. Okay, so for wind erosion, for the existence of desert environments, there are a few factors that have to be present, and mostly the because of wind erosion, what happens is all the finer fertile material that that is present on the top part of the earth's surface is actually blown away by the wind, and it gets deposited at some other area, and what you are left with is very rocky, barren kind of a landscape. Okay, so this is one of the effects of wind erosion itself. And obviously the erosive activity as well as depositional activity, both of them are very much significant when we are considering aeolian geomorphic processes. So the wind erosion happens by two processes, deflation and abrasion. So deflation is where all the finer sediments are actually blown away by the wind, and what you are left back are the coarser rock material. And abrasion happens when the sediments or the material that is being transported by the winds are actually eroding because of the frictional action between the material that is carried by the wings as well as the rocks or features that the wind actually kind of intercepts during its movement. And you can have grooves and scars and grinding of rocks that happen due to the erosional activity that is carried out by the wind because of the sediments that are being transported by the wind. So deflation causes two kind of features. You have deflation basins and desert pavement. So in deflation basins, you can see over here all the finer material is actually being is blown away by the wind. Okay, and what happens is the base level, the ground level actually intersects the aquifer over here, and you can have oases and swarms that are forming. Desert pavement is formed when the obviously the finer material is blown away by the wind, and the coarse and the concentration of the coarser material actually increases, and finally only coarser material is seen on the land, and all the finer sediments are kind of buried under these coarser sediments, and this is called desert pavement, and this also makes up the rocky deserts that we see. Then wind erosion activity, that is the abrasion action of the wind erosion actually forms features like ventifacts, where you can see that one part of this rock fragment has got polished. Then you have yardangs. So in yardangs what happens is when you have alternating softer and harder material, so the softer material between two harder material actually gets eroded, and what you are left with are these parallel kind of features with troughs in between, and these are called yardangs. And zoogain is when there is alternating horizontal layers of harder and softer rocks, and these softer layers get eroded easily compared to the harder rock, and what you are left with is this tabular mass or tabular feature in between the desert. Now, wind depositional landforms, so wherever where the winds have actually deposited the sands, they try to move or transport this sand from one place to another. So either this happens, this happens very gradually, and we can see some of the kind of patterns that are formed on in desert areas, which gives us the understanding of the direction of the wind also. So sand ripples form where the the smaller grains are transported away, and the larger grains actually form kind of small wave like features. And ripples, there are sand ripples where the grain differences are seen, and ripples are usually found in the slopes of the dunes itself. Okay, so they are easily moving, but they do not move greater distances. They move over one side of the dune itself. Then you have the wind blown dust. So these are dust sized particles that are carried with the wind and in suspension, and so the sand sized particles can travel locally, but finer size finer size material in the wind itself can travel larger distances. Okay, so that is the wind blown dust. Now, the most important landform that we have are the dunes. Okay, so the dunes are formed with the crest being kind of perpendicular to the direction of the wind, and this is the windward side of the slope, and this is the leeward side. Okay, so the windward side is the has a gentler slope, whereas the leeward side has a steeper slope, and with time the sand can actually move from the windward side and get deposited in the leeward side, and kind of uh, this shows that the dune can actually move forward because of the transport and deposition of the sand from the windward side to the leeward side. So, the dunes can actually increase in size and travel from one place to another in that. So, in case of how they can travel, you can have free dunes, the dunes which can travel with time, and then you have anchored dunes. So, these dunes are due to the either the vegetation or the topography, they cannot move. So, wherever they are forming, the crest remains there, and some part of the dunes can move, but not the entire dune. So, the types of dunes that we have are Barchan, parabolic, transverse, longitudinal and star dunes. So, you can see over here Barchans are like these crescent shaped dunes, and this is the wind direction, and the crest is perpendicular to the wind direction. And for parabolic dunes, these mostly occur in coastal regions or areas where there are vegetation presence. So, what happens is the crest of the dune does not move, but these wings, okay, so these wings of the dunes can move and get longer, and hence they form like a parabolic shape. Over here you can see that the leeward side of the dune is actually facing the wind. Okay, why? Because the parabolic dunes are formed due to the blowout, the formation of blowout. So, over here, since the vegetation is present here, and this part is actually open for the wind erosion. So, this material actually gets blown out, and what you are remaining with is the sand that below the vegetation and the slip face over here. Okay, so this is formed in a way opposite to the formation of the Barchan dunes. Then you have the transverse dunes. Okay, so these are again linear ridgy sandy dunes, and they are perpendicular to the wind direction. Okay, longitudinal dunes are those which actually form in the direction of the movement of the wind. Okay, so they are formed in the parallel, parallel to the wind direction, and they are also called as sieves. Okay, because they have, knife like edges are formed because on that. And then you have the star dunes. So, star dunes is when you have a mound of sand that has got deposited, and it is actually being affected by winds coming in from different directions. So, you can see over here, you can have different numerous arms of the dunes, and you can have, pyramid shaped dunes also, and they are irregularly shaped because the wind direction changes a lot in areas where star dunes are formed. So, that is it for today's class, and obviously these notes will be put up in the by the NPTEL team, as well as the recording of this lecture. So, hopefully these sessions have helped you in understanding the weekly course content, and obviously the entire field of the geomorphology as a whole, and how different geomorphic agents shape the landforms and landscapes. And thank you so much for attending these lectures and giving your kind attention, and all the best for your exams. If you have any doubts till the time you have your exams, please put them in the discussion forum. So, either me or any of the NPTEL course team member will answer it for you. So, thank you so much. All the best.